The chapter 3 talk about the algorithm and the time complexity of some common algorithm. For example, sorting, searching. So for the next example, we want to find the value 4 in the similar way. Not. Because it is not equal to the last term. So here I is n. The index out of the array. So in this here, we do not write down h in the second h. So in this here, we return -1 out of the array. No, we will consider another searching algorithm. We call the searching binary search algorithm. We can see the second here increasing order. We start by comparing the element to be located at the middle of the list. We need to locate the middle, left plus right divide 2. So here we use the floor function. Did you remember the floor function? We have 0 plus 15 divide 2, 7.5. And the floor is 7. We do a comparison h with the element at the middle. Because here the middle less than h. In increasing order array, the middle 10, and we want to find s in this second because it's greater than the middle. So we should find h in the upper half. The list is then split into two smaller sublets of the same size. The first one contains the element less than h, and the second one, the upper half, contains the element greater than h. Now we restrict the search to the upper half because here h is greater than the element at the middle. So we try to the search from A to 15. So here we set left is 8 and right is 15. In the similar way, the middle is 11, and the element at the middle is 16. So now we do a comparison 16 with h. Because 16 is less than h, we will restrict the search. This is step ID. The first step, at the beginning we have the left 0, the right 15. So the middle is 7. And the value of the middle is 10. So because the middle less than h, we turn the left from 0 to the middle plus 1. So in the next step, we search from 8 up to 15. We have at the middle 11. We search in this sublist because h greater than the middle. We search from 10 to 15. The middle 13. The element is and h is the equal. We stop the searching here and we return the index 13. The searching stop here by this statement. The binary search algorithm is more efficient than the linear search algorithm because after each step we restrict the search in a half. In the first step, we search in the array of length n. And the second step, we just search in the subarray, the length of n divide 2. Next step, so the length is n divide 4. In this here, we have n 16. So this is 16, this is 8, this is 4, 2, this is the length of 1. We do the first step, second step, 3 step, 4 step, 5 step. So in the worst case, for the binary sort, if the array has the length of n, we need at most logarithm n, maybe plus 1. We have the complexity of O up to n. In here, in the worst case, for linear searching, we have to do n comparison. We can say that the complexity of linear searching algorithm is On. In the worst case, the complexity of the binary searching algorithm O log 2 of n. The binary search algorithm is more faster than the linear search algorithm. Just keep in mind that the sequence of the list has the increasing order. We consider the problem of sorting. Sorting is putting these elements into a list, which elements are in increasing order. There are many sorting algorithms. Some algorithms are efficient than the other algorithms. Sorting is an important problem in computer science. The bubble sort. This is one of the simplest sorting algorithm, but not efficient. The bubble sort puts a list into increasing order by comparing adjacent elements. This is a pair of adjacent elements. Because 3 greater than 2, so we swap. So here we have 2 and 3. Because 3 less than 4, here we do not swap. And the next, because 4 is larger, so we swap. And the last check, because 4 less than 5, so we have no swap. After the first pass, we have the array here. We go to the second pass. We do comparison, not swap. And the next, because 3 greater than, so we swap. And then we do not swap. In the end of the second pass, we have the array is here, the first part. In a similar way, we swap here, then no swap. In the second pass, we drop out the last element. We check the index 0, 1, 2, 3. This is the last pair because 5 is a lot. Here in the third part, we drop out 2 elements. So this is the last pair. So here we just have 2 elements. Because 1 less than 2, the bubble sort complex here. We try to consider another sorting insertion sort. This is also a simple way. So I want to say about the idea. This is the sequence. And the first step, we have the sequence of length 1. And the second step, we want to insert A of 2 into L. We have 2 elements in increasing order. So in the next step, we try to insert A of 3 into suitable position. After the step 3, we have the list of length 3 in increasing order. So in the next step, we try to insert AN to the list of length N1. Here, the list is the first term. We insert 33. In the next, we try to insert this into here. So we do not have to insert because 84 is greater than the end of this list. In the next, because 49 is less than 84, so we set. Okay. And then we compare with here. Because this element is less than this element, so we shift the element to the right. And here, because 49 is greater than 33, so we stop here. When we stop here, we replace the element at the index. Okay. Here we have A1, A2, A7, and A7. So we have 6 steps. To solve many optimization problems, one of simple and efficient ways is to use greedy algorithm. We will talk about the greedy algorithm later. Okay, so now we talk about the crowd of the function. We want to estimate the time required to solve a problem. Because the time depends on the number of operations, it also depends on the hardware, the software. We can approximate the time required to the number of the operations. We have two problems about the complexity, the time complexity, the space, the memory complexity. Because the space depends on the data structure, we do not talk about the data structure, so we focus on the time complexity. We restrict the complexity of algorithm to the number of basic operations. We consider here the bit O notation. Let f of h and g of h be two functions from the set of integers. We say that f of h is bit O of g of h if there are two constants. F of h grows slower than some fixed multiple of g of h as it grows. For example, here we have h of h is O of h squared. We need to draw that f of h then equals c of h squared. Because 2 times of h less than 2 times of h squared. Whenever h greater than 1. So h squared is greater than h. And then we have h squared greater than 1. H squared is the same. So we can see that f of h less than or equal to 4 times of h squared. For h greater than 1. So here we can say c is 4. So here, as we can see in the figure, for h greater than 1, we have f of h then 4 times of h squared greater than or equal h squared. We can see c, so we can say f of h is bit O of h squared. For on h greater than or equal to 1, we can say h squared is O of, or we can say, in this case, we can choose c is here. We can take c is 1. We are saying f of h is a bit O of g of h. We can replace the function g of h with the function h of h, such that h of h greater than g of h. And so we can say h of h is a bit O of h of h. H of h is bit O of h squared, because h squared less than h power of 3. So we can replace the g of h with h of h, and then we have h of h is bit O. However, we should choose the function g to be as small as possible. So in this here, we can choose, but maybe we should choose a square. Here we can see some big O estimate for some important function. This is a display of the growth of function commonly used in big O estimate. Here we have the arithmetic progression. We can evaluate because 1 is less than n, 2 is less than n, and the last n is less than or equal to n. So we have this summation is then or equal to n squared. We can say that 1, 2, 3, 2, n is big O of C1 for h greater than 0. This is a polynomial, so we can prove that this polynomial then h of n c h of x is big O in n. For the next example, the factorial. In the similar way to the first one, we can see that n factor less or equal to n power of n. So we can say n factor is big O. We can take c is 1 for n is greater than 1. We consider the growth of combination of functions. Suppose that h1 of h is og1 of h and h2 of h is og2 of h. We have the sum of the two functions is big O of the maximum of g1, g2. For the product, we have the product also. In computer programming, many algorithms are made of 2 or more sub-procedures. It is often necessary to estimate the growth of the sum and the product of two functions. We have the big O. We also have the omega. The big O is upper bound. In some cases, we need the reverse. So we can say f of h is omega g of h. The big omega means the lower bound. So we have big theta. It means big omega and big O. So we have f of h is the same order with g of h. So the time complexity it turns up the number of operations. Because we have many operations, so we just focus on the basic operation. For example, if we want to analyze the complexity of the linear algorithm, we should focus on the comparison. Here we analyze the time complexity in the work state. In the case we cannot find out h in the length, we have the maximum of comparison. The comparison in this here n plus 1. The best case means we just compare h with the element at the position 1, and the comparison is true. It means we find out h in the first element. So we just do one comparison. But it's good to focus on the worst case. So in the worst case, we cannot find out h in the list. So we have to do n plus 1 comparison. What is the big O of n plus 1? The big O is n. You can answer on square, on3, but the best answer is on. The worst case analysis tells us how many operations an algorithm requires to guarantee that it will produce a solution. Besides the worst case, sometimes to know the complexity in the every case, so we want to know the average number of comparison used to solve the search for all possible input array and H. X can occur here. So if occur here, we have one comparison. If occur here, we have two comparison. If H occur in the I position, we have two I comparison. It can occur here. So we have an operation. So we need to compute the sum and we divide to n. In the every case, we need to consider a random input. Did you remember this summation? This is an arithmetic progression. So we have n times of n plus 1 divide 2. Here we have to divide n. The result is n plus 1 divide 2. The average comparison number is without of what? N, maybe n, okay. So C is 5 and K is 1. Again, C and K is a witness. The average complexity of the linear subalgorithm is big out of n. This is the conclusion. To analyze the time complexity in the average case is more important, but usually much more complicated than the worst case. To review the growth of the function, you can see here, this is O log n. We have the binary algorithm for O(n). We have a linear search algorithm. For O(n) log n, we have a quick sort for n squared. We have a buffer sort, the insert sort. Again, the buffer sort. In the first part, we compare two adjacent elements. We determine the maximum and we drop out the array. So for the second pass, again, but we stop here, not stop here. So and then we drop out this. And the last step, just stop here. How many comparisons? 1 pair, 2 pair, 3 pair, and the last pair. This is the number of comparisons in the first part. In the second pass, in the third one, okay. And the last step, we have only one pair. The summation is n 1 and the time 2. It's all n squared. So all 2 power of n, we have Hanoi Tower. You know the Hanoi Tower problem. Factorial complexity. This is the logic complexity. To compute the factorial, so we have the increasing order of the complexity. What is the base O of the f of it? The f of it is a constant here. 1, because we can take C, so we can say f of h is base O